Hello, and welcome back to the Cracking FAANG YouTube channel. Today we're solving Leetcode problem 1740, find distance in binary tree. Given the root of a binary tree and two integers p and q, return the distance between the nodes of p and value q in the tree. The distance between two nodes is the number of edges on the path from one to the other. So let's look at an example. We have this binary tree here, and we want to find the distance between the node p and the node, p equals 5 and q equals 0. So that's this node and this node. We can pretty easily see that we go from 5 to 3, that's 1. From 3 to 1, that's 2 steps. And then from 1 to 0 is 3 steps. So that's how we get our solution of 3 here. So this problem is pretty straightforward if you're just looking at the graph. Like, your brain can very easily solve it, but how do we do this in code? So there's two approaches here, and I'll kind of say both of them and we'll code one of them up. The first one is the least common ancestor approach. So what we want to do is in the graph, we'll find each node and then we'll basically find the lowest common ancestor of them. And we'll keep the distance to the lowest common ancestor. So if you remember, we solved the lowest common ancestor problem on this channel, but basically we would find it, which is 3 here, and we're going to keep track of the distance of each node to the least common ancestor. So from this side it'd be 1, from this side it'd be 2, and then simply add them together and we get the solution. Now, some people on Leetcode say that this is a one-pass solution, but I don't think so because they're calling their DFS function to find both nodes. Now, if your tree looks like a linked list where it's like this, and let's just say it's really long, and Q is here and P is here, you're going to do a search all the way to P to find P, and then you have to do the same search to do Q. So people who say that it's one pass, this is not true because I think in this case you would have to do 2 passes because you're basically traversing the entire tree. If they're just one node apart and Q is the last node in this like linked list type tree, then you're actually going to do basically 2 passes through the tree. So anyone who says it's one pass, I'm not too sure about that one. Anyway, that's the least common ancestor one. I don't really like that approach. I would much prefer to do it as a graph. And we've done this question before. It's just been in a different word. So actually, we're going to build a graph which maps, I guess, like each node to all of its edges, node to its edges, right? So basically where from each place we can go. And in this way, we can basically just start our search at either P or Q. And then with the graph, we're just going to traverse it, traverse the graph, and then basically just BFS until we get to either P or Q to find, and then that is going to be our distance, and we simply return that. So that solution, obviously to build the graph you have to traverse the entire thing, so it's going to be big O of n to do that, and then potentially in the worst case it's going to be also a big O of n in the case that you have a graph that's like this, or a tree that's like this, where P is here and Q is here. You have to basically traverse all the way up this way and then all the way up the right side. So that's why it could potentially have to visit all the nodes in the worst case. But at the end of the day, the time complexity is still going to be big O of n, same with the LCA. And then also the space complexity is also going to be big O of n for the graph. And then, yeah, for your BFS, you're also going to need big O of n. So it's just big O of n plus big O of n, but asymptotically, it's also just big O of n. So yeah, you have 2 options here. Again, you can go with the least common ancestor approach, or you can go with the graph approach. Personally, I like the graph approach. The time complexities will be the same, space complexity are the same. I think explaining the graph is a bit easier, but this is just a good example that for one question there are potentially multiple solutions, and in an interview it's actually good to list them out, and then you can just go with whichever one you want. Obviously, if one was more efficient than the other, then you should do the more efficient one, but in the case here where they're the same time and space complexity, I'm just going to go with the graph solution because I like that one better and it's easier for me to explain. So again, we're going to build a graph of basically all the nodes we can reach from a given node, and then we're just going to start our BFS from, let's just say, P, and we're going to BFS until we get to Q, and then however many steps it takes, that's how long it is between them. So that's how we want to solve it. Let's go to the code editor and type this up. Okay, so we went over the intuition, we went over 2 possible solutions, and now we're going to code one of them up. First thing we want to do is let's just clear away all this kind of boilerplate and just have a clean working environment. So first thing we need to check is actually if p equals q, we don't need to do anything. Obviously the distance between two nodes which are the same are going to be 0, right? And one thing that we need to actually realize if we look at the constraints of the problem, I probably should have said this before, is that all the values are unique and that p and q exists in the tree. So if p equals q, oops, how do I get rid of this? Okay, fold. Then we're done. So if p equals to q, then we return 0 because of the same node. Okay, so we want to build our graph. And remember, we're going to be mapping for each node, basically all the other nodes that you can reach in that tree. So we're going to say the graph is going to be collections.defaultDict, and this is going to be a list. Now, to do this, we're going to have to BFS over our tree and basically build the graph node by node. So we're going to say we need a queue here to basically process everything. So we're going to say queue equals collections.defaultDict. Oh, sorry, not defaultDict. Deck. We want to use a queue. And we're going to pass in the root. Now we're going to say while we have something to process, if I could just type today, that'd be great. We're going to say the current node is going to be queue.popLeft. And now what we want to do is if the left node exists, then we want to populate that relationship in the graph. And also if the right node exists, we want to populate that relationship in the graph. So we're going to say if node.left, we're going to say graph of node.val. And the reason that we're storing the values here is because they're all unique. We don't need to actually store the nodes themselves. We can just store the values because they're guaranteed to be unique. We don't have to worry about any sort of duplicates or anything. So we can just store the values directly. So we're going to say there's going to be an edge, which goes from node.val to append node.left.val. And conversely, we need to do the opposite because it's bidirectional. So we're going to say graph of node.left.val. We're going to append node.val. And then we just need to append that left node so it can be processed further. So we're going to say q.append node.left. Same thing for the right node. We're going to say if node.right exists, we're going to say graph of node.val. We're going to append node.right.val. And we're going to do the same thing for node.right.val. We're going to append node.val. Okay, so, and then the last thing we need to do is we need to make sure we do q.append node.right so it also can get processed. So doing all of this will build our graph. Now, obviously we need to process that graph. So we're going to do a BFS. We're going to start at node P and we're going to search for node Q. So what we're going to do is we're going to say a queue is going to be collections.deck and we're going to populate our deck with what? We're going to use a tuple and we're going to start our node at P. And obviously we've done 0 steps so far. So we're going to store that we've done 0 steps. Now, whenever we do a BFS, we want to make sure that we actually don't get caught into a cycle. Obviously our graph has bidirectional edges and we could actually go in a cycle if we didn't keep track of where we visited. So we're going to say a visited set is going to equal to set, and we're going to put P in there because that's where we start our search. Now all we need to do is just kick off our BFS, go from P, and then as soon as we hit Q, we can stop and then just return the number of steps we took. So we're going to say while Q, we're going to say the current node that we're processing and the number of steps we've taken is going to be q.popLeft. And we're going to say if the current node, it actually equals Q. And remember that the current node, we actually put the value in there so we can just compare it to Q directly because P and Q are actually integers. They're not given to us as nodes. So if the current node equals Q, we're done. We found Q. We can simply return the number of steps it took. Otherwise, we need to continue our BFS. So we're going to say for edge in graph of whatever the current node is. We're going to say if we haven't visited that edge, obviously we don't want to get caught in a cycle here. So we're going to say if edge not in visited, then we want to visit that edge. So we're going to say visited.add that edge, and we're going to say q.append the edge, and then steps +1, because now we need to go one step further. And that's actually it. We're done. So as soon as this return trips up, we will be done. There's nothing more we need to do. Let me just make sure I didn't make any syntax mistakes. And it looks accepted. Submit this thing, and it is accepted. Cool. So let us go over the time and space complexity. We talked about this earlier, but basically to build the graph is going to take big O of n time, and then to BFS over it is going to take big O of n time. So let's just do that. So we have the time complexity. So this is big O of n to build graph, and then we need big O of n to BFS graph. So this means that it's big O of n plus big O of n, which is big O of 2n, but we know that asymptotically this is the same as big O of n. Space complexity, it's the same thing. It's going to take big O of n to build the graph plus big O of n to BFS over it, because we need to maintain the queue. So again, this is big O of 2n, which asymptotically is just big O of n, which is actually the same runtime complexity of the least common ancestor solution. So both of them are the same. But yeah. Okay, so that is how you solve find distance in a binary tree. I quite like doing problems like this, where you basically take a binary tree, transform it into a graph, and then traverse that graph to get your answer. I really like that solution pattern. I don't know, maybe it's just years of working at Facebook and traversing graphs and nodes and all that. I just like graph problems. Anyway, that's how you solve it. If you enjoyed the video, why not leave a like and a comment, and subscribe to the channel. Really helps me grow. Otherwise, thank you so much for watching, and I will see you in the next one. Bye.